These are the notes on atomic stability. It will be helpful to have a periodic table handy as we go through these notes. All right, as we talk about atomic stability and what makes an atom stable, we want to remember the structure of an atom. So our particles that we have in an atom are protons, which have a positive charge, neutrons, which have a neutral charge, and electrons, which have a negative charge. When we're thinking about charges, what charges attract each other? Well, opposite charges are going to attract each other. And so that means protons and electrons are going to have an attractive force between them. What charges repel each other? Well, like charges are going to repel each other. So protons are going to repel other protons, and electrons are going to repel other electrons. We don't talk a lot about protons repelling other protons, but that's why we have neutrons in the nucleus as well to help with those repelling forces. Our electrons spread out in our subshells, and so that is, so it's because of those repelling forces. That's why our electrons will spread out before they end up pairing up. We're going to focus today on those protons and those electrons and that attraction that they have to one another. And when we're looking at this, where are those protons are in the nucleus, those electrons are in those energy levels. So if we're looking at this Bohr model of a nitrogen atom, what we're going to be talking about today is not only how many positive charges we have here, but also how far away they are. And so our negative electrons are some distance away from our positive protons if our electrons are in that first energy level. And then same thing with our electrons that maybe are in that second energy level, which are called our valence electrons in this case. So valence electrons are the electrons that are in the outermost shell of an atom. These electrons determine the atom's chemical properties. They participate in chemical reactions and bonding. And so we spend a good part of the beginning of our year talking about valence electrons. And so if we're looking at this nitrogen atom, we're only looking at the electrons that are on that outermost shell of an atom or in that highest energy level. And you should have labeled these on your periodic table, but we'll kind of reference those now throughout our notes. So most elements are stable with 8 electrons in their outer shell or in that highest energy level. So that's going to be something that we focus on throughout these notes. So what is that attraction called? That attraction is called coulombic force. And it is the attraction or repulsion of particles because of their electric charge and their proximity. We are focusing on that attraction part because we're going to be looking at the protons being attracted to the electrons. But coulombic force is also why the electrons repel each other and the protons repel each other with that. So we're going to have to focus on 2 things, the amount of charge and the proximity. The reason that this is called coulombic force is that a coulomb is what we measure charge in. And so it is just a force, a push or a pull, but it is because of that charge. One thing we can compare this to, since charge, electric forces aren't something that we commonly talk about very often, is that magnetic force comparison. And most of us are familiar with magnets. So those laws of magnets, if you have opposite poles that are towards each other, those are going to be attracted. And so if those opposites are closer, they're going to have that stronger attraction. And if you are looking at same poles, so south and south, if you have those together and they're close, they're going to have a strong repulsion. As those move farther apart, it's going to have a weaker attraction or a weaker repulsion. And that's why we can't really feel that push and pull with magnets if those are farther away, but we can feel that push and pull when we move them close together. So the same thing happens with our protons and our electrons. So we're going to focus on that proximity aspect with our that closeness of the electrons. And that electric charge, that's like the strength of a magnet. Do you have a strong magnet or a weak magnet? So looking at those 2 things, how can we look at and describe electric charge in an atom, electric charge, or another name for this is nuclear charge, is based on how many protons are in the nucleus of an atom, attracting those electrons to the nucleus, kind of pulling those in. So if we have more protons in the nucleus, it's going to be a stronger coulombic force. If we have fewer protons in the nucleus, it's going to be a weaker coulombic force. And this is in addition to considering proximity. And so when we're looking at electric charge, we really only focus on this if we're looking at coulombic force for elements that have valence electrons in the same energy level. So we would only look if we already know those valence electrons have the same proximity, then we would compare that nuclear charge or that electric charge with that. We use this when talking about reactivity as well. We can also, though, consider octets when we're talking about reactivity because this is what actually determines those behaviors. All right, coulombic force proximity. So proximity, how close your electrons are to your protons, or that distance between our protons and electrons. Distance is going to be determined by energy levels. So if you have an electron in a higher energy level, so energy level 4, 5, 6, those electrons are going to be further from the protons. If we think about that model of an atom, if this is my nucleus with my protons and my neutrons, as we have those energy levels, if we want to think of those like a Bohr model, the higher those energy levels are, the farther away our electrons are going to be from that nucleus. The lower that energy level, the closer the electrons are going to be with that. And so electrons being further from the protons means it's a weaker coulombic force, a weaker pull of those protons and on those electrons. If your electrons are in low energy levels, 1, 2, 3, those electrons are closer to the protons, so that coulombic force is going to be stronger. So what electrons are going to have the least amount of coulombic force? Well, when we're dealing with our atoms, they're going to have these full inner shells of electrons. We only have to look at the electrons that are the farthest away, which would be our valence electrons. And so we're going to consider where are our valence electrons when we are describing how close our electrons are to the nucleus. So here's a periodic table. On your periodic table that you labeled, you should have labeled the energy levels. And so these energy levels are what we're going to use to talk about what energy level the valence electrons are in. We also should have labeled our valence electrons across the top. And notice it only goes up to 8 valence electrons because that's where our atoms are most stable at for most of our atoms. So we're going to go through some CERs, claim evidence reasoning, for answering these questions about strength of coulombic force. So here's one I kind of mapped out what our CER might look like. So does magnesium have a stronger or weaker coulombic force than strontium? So I'm comparing those two. If I'm not sure what my answer is, let's gather our evidence. So magnesium has how many valence electrons and in what energy level? So let's grab our periodic table. We've got magnesium right here. So it has 2 valence electrons in energy level 3. And then let's do the same for strontium. Strontium is Sr, it's right here. It has 2 valence electrons in energy level 5. And so now I need to consider my pieces of coulombic force, my proximity, and my amount of nuclear charge. Because these are in different energy levels, we're going to use those energy levels to compare it. So I don't have to actually list that magnesium has 12 protons and that strontium has 38 protons, because this proximity, these are at different energy levels. So we're not going to use the protons to compare coulombic force in this case. So if we look at this, I'm looking at this and I see that strontium's valence electrons are in a higher energy level. Our nucleus is kind of up here, and then here are our rings of energy levels of electrons. Magnesium is closer than strontium, which means that magnesium is going to have a stronger coulombic force than strontium. So as we are looking at explaining this, we want to use what we know about a coulombic force, and that it's an attraction, and that if those valence electrons are closer, it's going to increase my coulombic force. So let's look at our reasoning. Since magnesium's valence electrons are in a, and I like using comparing words here, lower energy level, I don't need to restate my evidence because it's already up here so that my reader can look at it. Since they're in a lower energy level, there is greater or stronger, either would work, coulombic force as the electrons are closer to the nucleus and experience more attraction between charges. And if we wanted, we could get rid of that, then strontium's valence electrons there. So those things that I want to mention the energy levels. That's what's telling me that distance. So I need to say, compare those energy levels. I need to say the electrons are closer if they're in a lower energy level. And so that means there's more attraction and a stronger coulombic force. So putting together kind of the definition of coulombic force and how we can see those things in our data. So your evidence for anything where we're using coulombic force or periodic trends, evidence is going to be information from your periodic table. All right, answer for that one is there as well on your next slide. Go ahead and take a minute to, if you want, pause so that you can try this one on your own, see what you can fill in, and then come back and I will fill it in with you. All right, so does phosphorus have a stronger or weaker coulombic force than sulfur? So with this one, kind of looking at what I have, sulfur has how many valence electrons in what energy level? So sulfur is over here on the right, 6 valence electrons in energy level 3. And phosphorus has 5 valence electrons in energy level 3. So as I'm filling those in and I'm looking at coulombic force, one thing I'm noticing is that these are in the same energy level, which means it's going to be the same proximity, that they are the same distance away from the nucleus, which means we now need to consider our nuclear charge. So nuclear charge is going to be us looking at our protons. So I can go to my periodic table. Protons are the atomic number. So sulfur has 16 protons, phosphorus has 15. So sulfur is going to have 16, phosphorus has 15. So now I'm comparing that those valence electrons are the same distance away, but which one of these is going to have more charge to increase or decrease that coulombic force? So sulfur has 16 protons. It has more protons than phosphorus, which means that sulfur is going to have a stronger coulombic force than phosphorus. So addressing that proximity, sulfur and phosphorus's valence electrons are in the same energy level. Since sulfur has more protons, it has a greater or stronger nuclear charge and therefore a stronger coulombic force than phosphorus with that. So more nuclear charge is going to be a stronger nuclear force. Less nuclear charge is going to be a weaker nuclear force as long as those energy levels are the same. If those energy levels are different, we're going to use the energy levels. All right, take a minute and try number 3 on your own and then come back and here's my answer. All right, so phosphorus has a weaker coulombic force than nitrogen. My evidence is valence electrons and energy levels here. Again, notice this one, we have different energy levels And so because that phosphorus was in a higher energy level, it's going to have a weaker coulombic force. All right, moving on, we're going to talk about reactivity a little bit. So the octet rule, elements are most stable with 8 electrons in their outer shell. We are going to use this when we talk about reactivity. And this is also why when we've seen charges of atoms, it's been to kind of fill an octet or empty an octet, because it's the valence electrons and that octet rule that determine the charge of a atom or of a charged particle. So remembering our definitions of ions. And so alkali metals, when they're ions, all have a +1 charge. So if we look, our alkali metals are in group 1. They have 1 valence electron. It's going to be easier for them to lose 1 valence electron so that the shell below them is the full outer shell, which means that if they lose 1 electron, they're going to have a full octet, but losing 1 electron leaves them with a +1 charge. Halogens, when they're ions, all are going to have a -1 charge. Halogens all have 7 valence electrons, so they can easily gain 1 electron to get that full octet. By gaining that electron, they're going to then have a -1 charge because they have an extra negative electron. And so these valence electrons determine our properties of reactivity. We're going to look into that in our lab. And so these are kind of a reminder of things that we talked about when we were filling in the periodic table notes. So take a second and read through those. One chunk of the periodic table where we don't know their valence electrons is the transition metals, and that includes under the staircase. That middle valley on the periodic table is our transition metals. We cannot determine their valence electrons from the periodic table because those valence electrons can vary. And those are less reactive than our other metals, just generally because of those unknown valence electrons. All right, so there's a periodic table again. We are going to do a CER together, talking about reactivity and that octet. We'll do one together, and then there's one for you to practice. So using our knowledge of coulombic force, valence electrons and octets, will calcium be more or less reactive than potassium? So let's look at what we have. So calcium has 2 valence electrons in energy level 4. Potassium has 1 valence electron in energy level 4. Because those are at that same proximity, we need to compare protons. So calcium has 20 protons, potassium has 19. With that. So as we're looking at this, in order to get that full octet, both of these are going to have to lose an electron. So it's either going to have to lose 1 or 2. Potassium has to lose less, and so it is going to be more reactive. But as we look at it, it also has less protons, which means that in that energy level 4, the force on those valence electrons is weaker. So potassium has a weaker coulombic force because both of these need to lose electrons. That is going to make it so that potassium is going to be more reactive, meaning that calcium will be less reactive. And that's because our calcium has more valence electrons that it needs to lose to get to that octet. It has to lose 2 instead of 1. But it also has more positive protons that are going to be holding on to those 2 valence electrons a little bit stronger. So looking at our reasoning, calcium and potassium both have valence electrons in energy level 4. Calcium has a same energy level, but more protons, stronger coulombic force because it has more protons than potassium. Calcium will be less reactive because of its strong coulombic force, making it harder for calcium to lose its 2 valence electrons to reach a full octet. So these ones do get a little bit, there's a lot in there, because if we're talking about reactivity, we have to mention that full octet. We need to mention how that element is going to get there. We also, though, need to include talking about our valence electrons and our coulombic force. So we're kind of adding something else on there. So talking about that stronger coulombic force because of its increased nuclear charge. And so that's why it is less reactive, because it's harder to lose those electrons. Take a minute and try number 5 on your own. Pause this video and then come back and I will talk through my answer. All right, here's number 5. So will nitrogen be more or less reactive than oxygen? So nitrogen will be less reactive than oxygen. Nitrogen has 5 valence electrons in energy level 2. Oxygen has 6 valence electrons in energy level 2. And then I also have their protons because the energy levels are the same. Upon writing this, you may have flipped your claim. But if we think about this, how are both of these going to get to that octet? Well, nitrogen is going to need to gain, because it's going to be easier to gain 3 electrons than to lose 5. Oxygen is going to gain 2 electrons, because it's easier to gain 2 than lose 6, which means that that oxygen is going to be more reactive. It's closer to that octet. And so now it kind of flips our coulombic force because we are wanting to gain electrons. So nitrogen is going to be less reactive than oxygen. So looking at my reasoning, nitrogen and oxygen both have valence electrons in energy level 2. So that proximity is the same. Nitrogen needs to gain electrons to get a full octet, but because of nitrogen's weaker coulombic force, it is less reactive. So that weaker coulombic force, I could have also included in here that nitrogen has less nuclear charge. That probably would have been good. But I guess I said less protons, so that addresses my nuclear charge here like that. So that weaker nuclear charge for nitrogen means it's not going to attract those 3 valence electrons as easily as oxygen, which has that stronger nuclear charge and is going to attract 2 valence electrons more easily. Reach out to your teacher with questions. You're going to have time to practice these in your periodic trends lab.